prototype. So these are geometric similarity, kinematic similarity, and dynamic similarity. So now let us study these in detail. So geometric similarity means that the model and its prototype have identical shapes but differ only in size. Now the important consideration is that the flow patterns must be geometrically similar. When the shapes are identical, that for model and prototype, so the idea is that the flow patterns must be geometrically similar, means they should be subjected to the same conditions. The length scale ratio is defined as LR. This is the length scale ratio. This is length in the prototype divided by the corresponding length in the model. So the ratio of the linear dimensions of the prototype divided by the corresponding dimensions in the model. This is the length scale ratio. Now we can extend this to area and volume. It follows that areas vary as LR square and volumes as LR cube. So it means that when we have area, so for area we take two dimension. We have this AR, and because we have two dimensions, so that's why it will be equal to LR into LR. If we have the same scale ratio, so this will be equal to LR, this is square. Now for volume, let's say this is volume to differentiate between the two. So then in that case, this will be equal to LR into LR into LR, three dimension, because when we take volume, so that's why this can be written as LR cube. Now remember, we have to ensure this. If there is geometric similarity, then we have to ensure that in the all dimensions that we consider, there is similarity, means they are in the same scale. So this length scale ratio that we define, that is LR is equal to LP by LM. Now one thing I should mention here before I proceed is that if you study some other fluid mechanics books or hydraulics books where you study this similitude, so then in that case it may be written as that we have this LM linear dimension in the model divided by LP. So in some books you can find this ratio here. So this is then known as, can be denoted by lambda, and this is known as model ratio. This is known as model ratio. So this is known as model ratio or model scale, or we can call it as model scale. So actually this is not a problem. Either we write down LP by LM, which is known as the scale ratio. We consider the length, so we have length scale ratio. Or you can also use Lm by Lp, in which case this will be known as the model ratio or model scale. So for example, here we can write down 1:20. This Lm is 1 and Lp is 20. Clear? So this is the model ratio 1:20, or lambda can be equal to 0.05. This will correspond to a length scale ratio of 20:1. Here then we will write down 20:1. So we write down 1:20 or 20:1. This should not be a problem. Clear? So that's why in some books maybe you will find that they write down Lm by Lp. They write down in terms of the model ratio or model scale. But however, in our textbook, we will follow this convention here. We will write down the scale ratio, and that it will be equal to the, for example, length scale ratio. So it is equal to Lp divided by Lm. So we will try to follow this to be consistent with our textbook. Remember, this is chapter 7 of the textbook, similitude and dimensional analysis. This is chapter 7. I will share the soft copy. This is chapter 7 of the textbook, 10th edition. So now in this case, we define the length scale ratio. It means that this length in the prototype and in the model, this ratio is a constant. Clear? We will continue with this. You can see here that in the A part of the figure we see the prototype, and in part B we see the model. So now in this case, if you want to write down the length scale ratio, so this will be equal to LR. That will be equal to, for example, in here you take the dimensions. So this will be equal to LP divided by LM, and this will also be equal to WP as per the given dimensions here divided by WM, and this will also be equal to CP divided by CM. So this ratio will be a constant. Now, complete geometric similarity is not always easy to attain. You can see here that this ratio is a constant. Clear? But this is not always possible. Complete geometric similarity is not always easy to attain. Let me go to the next slide, where you see here complete geometric similarity is not always easy to attain. What is the reason? For example, for a river model, the horizontal scale is usually limited by the available floor space, and this same scale used for the vertical dimensions may produce a stream so shallow that capillarity has appreciable effect, and also the bed slope may be so small that the flow is laminar. So in case of river models, it's very difficult. We cannot ensure complete geometric similarity. Complete geometric similarity means that this is what you have written here, LR square, LRQ for the volume. It means that this ratio is the same in all the dimensions. We cannot ensure this. And for example, in case of, if we ensure this, it is better. Clear? But sometimes it is not possible. For example, the river model, the horizontal scale is usually limited by the floor space available. You have a facility of the laboratory. So there, in order to develop the model, we have to consider the space restrictions. So in that case, it says that if we adopt a scale for horizontal scale here, and then the same is used for vertical dimension, then what will be the problem? That in the flow becomes so shallow that capillarity has appreciable effect, and the flow can become laminar, where the flow in the prototype may be turbulent flow. So then in that case you use the model study to evaluate the prototype performance. It will not be accurate. Clear? So then in this case what we do, that in such cases a distorted model is used, which means that the vertical scale is larger than the horizontal scale. So then in that case, if horizontal scale ratio is denoted by LR and now the vertical scale is different, so the vertical scale ratio is by LR prime or dash, then the flow, the cross-sectional area ratio will be LR into LR prime. Earlier, what was the case? If we maintain complete similarity, then for the cross-sectional area, then we can use LR square. Clear? Then we can use LR into LR. Same. So LR into LR, we can write down LR square. Actually, this is better. We ensure similarity. Now, in this case, because of the problem that we cannot maintain the same scale ratio, the horizontal scale and the vertical scale, so then in that case, what we can do is that you see LR is not the same as LR prime or LR dash. So such type of model, these are known as distorted model. And still we are able to run test on river models. So sometimes complete similarity is not easy to attain. In that case, what is the option? That we use distorted models. Clear? Let us see a small video for this. So you can see here a distorted model of a river, and we want to simulate its performance. So this is how we do it. Clear? We ensure geometric similarity, but if it is not easy to attain, then in that case we have the option that we can use a distorted model, and still we will be able to predict the performance of the prototype. Next, we talk about the kinematic similarity. So kinematic similarity implies that in addition to geometric similarity, the ratio of the velocities at all corresponding points in the flows are the same. So what it means that all the velocities that are acting, now when the kinematic similarity is to be achieved, this will be in addition to geometric similarity, because if the shapes are different, then how we can ensure that the flow patterns will be the same? The velocity vectors that will occur as a result of the flows in model and prototype, that should be the same, only the scale difference. So that will only be ensured if we have geometric similarity. So it means that if kinematic similarity exists between the model and the prototype, this will automatically ensure that they are geometrically similar also. So in that case, the velocity scale ratio that we defined as VR is equal to Vp by Vm. So V is the velocity in the prototype Vp, and V is the velocity at the corresponding point in the model. Clear? And this is a constant for kinematic similarity. Now, in terms of LR, this is time is dimensionally L by V. You already remember this. S is equal to Vt. So time scale ratio that can be written as TR is equal to LR divided by VR. If you know the LR value and we already know the VR, we can determine the time scale ratio. Clear? These scale ratios that we define, you see here the length scale ratio, the velocity scale ratio, the time scale ratio. Also, we can have acceleration scale ratio. This will help us when we solve the problems, because in that case, you will transfer the results between the model and the prototype. So it will be asked that if the time taken by the fluid in the model is this much, how much the time will be taken by the fluid in the prototype. If the acceleration of the fluid is this much in the prototype, what can be the acceleration in the model, and vice versa. So these scale ratios, actually they will help us when we analyze the problems. Clear? So this is actually a topic also in your textbook, and a very big table is provided for the different quantities that we will study later on in this lecture. So there these scale ratios are developed, and these scale ratios for different parameters. For example, if you consider geometric, so it can be length, area, volume. If you consider kinematic, it can be time, velocity, acceleration, discharge. If it can be dynamic, then it can be mass, force, pressure, impulse, momentum, energy, power, work, etc. So because these, we have to transfer the results of model to the prototype and vice versa. So in that case, you will need these scale ratios. Clear? So that's why we need to understand fully these things. This will help us when we solve the problems. Clear? So for example, we have AR, acceleration. You can see here it is, what are the units here? Meter per second square. So that's why if you consider the model and the prototype, so this is actually LR, and this LR is actually LP by LM, and this TR, this is actually the time ratio in the prototype to the model. Whenever, remember, the subscript R is written, it means that it is the scale ratio. So this TR is also equal to LR by VR. Similarly, it can be written in this form also. So this will help us when we solve the problems. Clear? So kinematic similarity means that the velocities at all corresponding points in the flows are the same in model and prototype. So you can see here, that's why this is a constant. Vp by Vm. So scale ratio, remember. So we will stick to the textbook convention. We will write down prototype by model. Maybe in some books it will be written model by prototype. As I already explained here, it doesn't make any difference. You can see here, this is model ratio. This is model scale. So whether we write down in this form or in this form, it should not be a big issue. But you should know that some books follow one notation and other books another notation. Now we discuss dynamic similarity. Two systems have dynamic similarity if in addition to kinematic similarity, corresponding forces are in the same ratio in both. So we define the force scale ratio Fr, that is equal to Fp divided by Fm. Now these are the forces which must be a constant for dynamic similarity. So it means that the forces which are acting in the model and the prototype must be in this ratio here, must be constant for dynamic similarity. Now what are the forces? Now forces that may act on a fluid element include gravity force, pressure force, viscous force, viscosity, elasticity, surface tension. If the fluid element is at a liquid gas interface. You already studied about elasticity, volume models of elasticity, the surface tension in your fluid mechanics 1 course. So remember, these are the commonly encountered forces. There may be other forces. So the forces, remember, these are the commonly encountered forces. So we discuss them. But there can be other forces. Clear? Now, in dynamic similarity, it is in addition to kinematic similarity. It means that if we ensure dynamic similarity between the model and the prototype, it will automatically ensure kinematic similarity. And if kinematic similarity is ensured, it means that there must be geometric similarity between the two. So now we are coming to the forces. The force scale ratio, we define it here for the prototype and the model. Now remember, these are the common forces that we consider, but there can be other forces also. When these forces, remember, these forces that we consider, it's not necessarily that all these forces must be present in the fluid phenomena at the same time. No, this now we are discussing generally. So maybe it is possible that one or more forces are absent. This is what we have to understand, that what significant forces need to be considered in any specific fluid problem. If you fail to identify the important forces, then you will make mistake. Why? Let's say, for example, we have open channel flow. So we already studied that in open channel flow, gravity forces, they are significant. So if in a problem gravity forces are significant, and we consider, for example, surface force to be significant rather, then the model results will be not accurate. Clear? So this is actually very important step to identify what forces for a specific problem that will be important. And based on that, we have to ensure that this is used for considering the dynamic similarity. What I say, you will now understand in the coming slides. So this is important. This will not be given in the question that what forces are significant and then you proceed and then you use the laws of similitude and then you transfer the results between the model and the prototype. So remember, here the concept must be very clear. Otherwise, if you apply the laws without appropriate knowledge, then you will not get the desired results. Clear? This is important. So now these forces which are mentioned here, not necessarily all of them will be present at the same time. It depends on the flow problem. What type of fluid mechanics problem, hydraulics problem you consider, and then you have to identify, use your knowledge. These forces needs to be considered because they are significant. So for example, in case of pipe flows, so we already studied the flow is pressurized. So then in that case, Reynolds number must be important to consider for dynamic similarity. If you talk about open channel flow, then we studied that gravity is important consideration. So then in that case, the Froude number needs to be considered. You already saw we consider it in many open channel flow problems. Clear? So if you consider the Froude number in pipe flow problem, definitely the results will not be then accurate. So this is what I mean. You have to identify what forces are significant in the given flow phenomena, and then from there you proceed to consider dynamic similarity, apply the dynamic similarity, these laws of similitude, and then we can transfer the results between the model and the prototype. Now that we come to dynamic similarity, because if we have dynamic similarity, it will ensure the kinematic and geometric similarity. So that's why now our focus is coming to the forces. Now the forces that we just discussed, these are the common forces. Remember, as I say, there can be other forces also. So if the sum of forces on a fluid element does not add up to zero, the element will accelerate in accordance with the Newton's law. This is what you studied in mechanics, that sum of the forces on a body should be equal to zero. Now that is another condition. We have equilibrium conditions, static conditions of equilibrium, we have dynamic conditions of equilibrium. But in general, what we say that if summation of forces is not equal to zero, so it means that there is some net force acting. So that's why we say that the element will accelerate in accordance with the Newton's law. Now, if we want to balance it, so such an unbalanced force system can be transformed into a balanced system by adding the inertia force. So we find that many systems in nature, they are balanced because this inertia force is by default, because whenever there is a motion there will be inertia force. So that's why a balanced system, if you want to make by adding the inertia force, that is equal and opposite to the resultant of the acting forces. What we want to say is that if we consider the forces, the gravity force, pressure force, viscous, elastic, surface tension, so you get a net resultant. Now if this net resultant is zero, so equilibrium is ensured, summation of forces is equal to zero. So what we can do here is that we can add the inertia force, which will be equal and opposite to the net effect of these forces. So when you add up this inertia force here, then we can write down this as equal to zero. So the system is now balanced. That's why you see that this inertia force will be most of the time present. You see the Reynolds number, inertia force by viscous force. We studied the Froude number. What was that? Inertia force by gravity force. So you can see here that this inertia force, that is equal and opposite to the resultant of the acting forces. Now with this understanding, we see that these forces can be expressed in different terms. the common forces that we will consider. So you see that the gravity force, this will be equal to F is equal to mg, and it can be written in this way, because you already know that this density, that is equal to mass by volume. This is equal to mass by volume. So now mass is equal to rho into volume LQ into G. So you should understand this. You have already studied all these things in detail so far. So this is the gravity force. The pressure force, that will be equal to delta P into A. So this can be written as L square. And similarly, we have the viscosity. So that is in accordance with the Newton's law of viscosity, can be written in this way. We already discussed the Reynolds number and Froude number in case of gravity forces in open channel flow. We have the elasticity. So we already studied about the elasticity in your fluid mechanics 1 course, also the fluid properties, and also we consider this volume models of elasticity in the previous course also, when we study about the water hammer, where we consider the fluid elasticity. Clear? So in that case, you see that this will be equal to EV into L square. Why? The reason is that this EV, volume models of elasticity, what are the units of this? It has essentially the units of the pressure. So that's why force by area, this can be written as EV into L square. Similarly, we have the surface tension. So the surface tension, that is force per unit length. So F by L. In our textbook, it is denoted by sigma, the surface tension. So F is equal to sigma into L. And we have the inertia force that we already discussed when we try to develop the Reynolds number. This is in accordance with the Newton's second law. F is equal to ma. So this can be written as rho v square into L square. So these equations actually we will use to define certain dimensionless numbers. We already discussed two of them. One is the Reynolds number and the second one is the Froude number. Now here we will discuss some more dimensionless numbers due to presence of these forces. So this we have already studied. Now if we consider two systems, these are the two flow systems with geometric similarity, kinematic similarity, and dynamic similarity. So now when we talk about the dynamic similarity, it will ensure we have kinematic similarity, we have geometric similarity. Remember, that's why we are mainly now focusing on ensuring the dynamic similarity between the two systems. And now for the dynamic similarity, we come to the forces. Clear? That the forces, for example, the gravity force, prototype, and in the model, the pressure force in the prototype and the model, the viscous force, inertia force. So this ratio must be a constant, which is FRs. What is FR? Force scale ratio. So this must be a constant. Only then we can say that we have dynamic similarity. Now you see that for this system, we consider the four forces. What are the four forces that we consider? Gravity, pressure, viscous, inertia. That's why I say that this is in general, we discuss these forces. We have to determine that what forces are significant in what given fluid mechanics problem. It is not that in every problem we have to consider all these forces as significant. This is important. So now let's say we consider these four forces. Now what we can do here is that these can be expressed as force of inertia divided by force of gravity for prototype is equal to force of inertia divided by force of gravity for the model. We can write down in this form. The above equation, if we agree that for dynamic similarity, this is the situation, then we can also express the above equation in this form. We can write it like this, and we can write down like this: inertia force by pressure force for the prototype must be equal to this ratio in the model, because this is what we say, this is a constant for dynamic similarity between the two systems, model and prototype. And it can be also written inertia by viscous in the prototype, this ratio is the same in the model. Now you see that if we consider a 4 forces system, then we have to satisfy these 3 equations that we get. So similarly, we say that with 3 forces, if we consider in a system, then we have to satisfy 2 independent expressions, and so on. So for 4 forces, 3 independent expressions we have to satisfy. Only then dynamic similarity will exist. And when we have dynamic similarity, then we can transfer the results between the model and the prototype. These are now the laws of similitude. With these laws, we can transfer the results from the model to the prototype and vice versa. This we have to ensure. And when we have dynamic similarity, it will ensure kinematic and geometric similarity already. Now, you see here, we already studied that this inertia force by gravity force, this is actually what? This is actually the Froude number. So now it means that the Froude number, if it is the same in the prototype and in the model, remember the value, then we will say that dynamic similarity exists between the two. If you remember this inertia force by viscous force, so this is actually the Reynolds number. So it means that if Reynolds number is the same in the model and the prototype, then in that case, we say that dynamic similarity exists between the model and the prototype. And this inertia force by pressure force, clear? This is also a number. This is also dimensionless quantity. Why it is dimensionless quantity? Because it is the ratio of 2 forces. So the units cancel out. That's why you see here Froude number has no units. Reynolds number has no units. And this ratio, inertia force divided by the pressure force, so this is actually the Euler number. We will study this in detail in the coming slides. So this is the Euler number. This is what we have studied so far, the Reynolds number and the Froude's number. So now essentially we are coming to the dimensionless numbers that some we studied already and some we are going to study now. So now in simple words, we are now simplifying our discussion. Now let's say that if we have Reynolds number that is significant in any fluid problem, let us only consider the Reynolds number. So if we want to ensure the dynamic similarity between the model and the prototype, the Reynolds number in the prototype must be the same as the Reynolds number in the model. This we have to ensure, because if we ensure this, then we will say that dynamic similarity exists between the model and the prototype, and we can transfer the results between the two. Now this Reynolds number equal does not mean that, because we already studied that this Reynolds number in case of, let's say, pipe flow, we already studied, you remember, in case of pipe flow, this is equal to velocity into the diameter and then divided by the kinematic viscosity nu, or rho Vd by mu. So now we are not saying that the diameter will be the same in both. We are not saying that exactly velocity will be the same in both. Now we are also not saying that the fluid must be the same for both. Same fluid. We only say that whatever the proportion is, their result should be the same. Means that, let's say, if the Reynolds number in the prototype is 4000, just an example. So this must also be 4000 in the model. This is what we say. Now this does not mean that the diameter of the two should be the same. No. These can vary so that the product should be the same. This is exactly what we say Q is equal to A1 V1 is equal to A2 V2. Now we are not saying that these must be the same at the two sections, but their product can be the same. This is one. Now we are not saying that A1 should be exactly same as A2. No. All we say is that their product must be the same. But this is what we say also here, that they may have different proportions for velocity, forces, and other parameters that we consider, but this should be the same in both. If this is the case, then we will say that dynamic similarity exists between the model and the prototype, and only then we can transfer the results between the two. This is important. So now that we have to ensure dynamic similarity, it will automatically ensure the kinematic similarity and geometric similarity. We have to consider the forces, and now from the forces we have come to these dimensionless numbers. So now our main focus will be on these dimensionless numbers. So Reynolds number we already studied. I will not explain it in detail. We already studied about this. We know that it is the ratio of inertia forces to the viscous forces. And if you simplify, this is equal to LV by nu, which is the kinematic viscosity. Now this L is a characteristic length, any significant length in the model and prototype that we need to consider. So this L for the pipe flow we consider to be diameter. Now for any consistent system of units, this is dimensionless number. As I already said, it is the ratio of two forces. So force, units cancel out. So that's why it turns out to be useful for comparing different flows. Clear? We do not worry that what will be the situation if we have SI system or we have British gravitational system. So that is the advantage of these dimensionless numbers, that they are independent of the system of units. We can use them in any system of units. Now the linear dimension L, it may be any length that is significant in the flow pattern. So for a pipe flow, if you remember, now this chapter is not only about the open channel flow. Open channel flow chapter is now finished. Now we are discussing this similitude. So here the problem can be a pipe flow problem, the problem can be open channel flow problem, the problem can be any other fluid mechanics problem. So now for pipe flow, we already studied that it might be either the diameter or the radius. We already studied this. And in that case, the Reynolds number, this characteristic length L, this is considered as the important parameter, the diameter. Now, if two systems, such as a model and a prototype, or two pipelines with different fluids, are dynamically equivalent, clear? Equivalent term we are using. See carefully, we are carefully using the words equivalent. They are not exactly equal, equivalent. We can say they are dynamically equivalent. So far as inertia and viscous forces are concerned, they must both have the same value for R. Clear? So what we say is that in the model and in the prototype, these values must be the same. If this is the same Reynolds number as I already explained in the previous slide, then we say that the two systems are dynamically equivalent. Clear? Now we are not saying that this nu and nu must be the same, v must be the same, L must be the same. What we say here is that this Reynolds number must be the same in model and prototype. Then we can say that the two systems are dynamically equivalent. So the fluid used in the model need not to be the same as that in the prototype, provided L and V are so selected that they give the same value for R in model and prototype. This is what we have to take care. Clear? Now in this case, the fluid can be different. Clear? This fluids that we use for model may not be the same as in the prototype. Clear? So this Reynolds number that needs to be the same in the model and the prototype, then in which case we can say that the two systems are dynamically equivalent and we can transfer the results between the two. When we solve the problem, you will see how we transfer the results. So important concept in this here is that when we consider the Reynolds number to be significant and we consider dynamic similarity between the two, you must have to use your basic knowledge that is Reynolds number significant for this given fluid mechanics problem or not. Because let's say if Reynolds number is important, you need to consider for results interpretation or transferring the results, and instead you consider the Froude number, which is also a dimensionless number. You just say that, okay, I just need to consider the forces, gravity may also be present. So then in that case, the results will not be accurate. So this is important. This will come from the basic understanding. If you do not have the basic understanding, then there is this concept is not that straightforward. Clear? Let us see a small video here. Now you see here that we have a fluid and the Reynolds number is 0.3. See the effect here, it immediately stops. Now the Reynolds number is 30. If we stop it here, so you can see here the difference of the flows with the increasing the Reynolds number. So in such type of flows, you see that we have to consider the Reynolds number is significant dimensionless number when we analyze the problem. So this is important, remember. And this will not be given that, okay, these are the significant forces you need to consider in the model studies. This we have to use our basic knowledge to identify that what forces can be significant and must be considered in the analysis. The second one is the Froude number. The Froude number, we also studied about this in the previous chapter that we studied open channel flows. So we already know about this, that it is the ratio of inertia forces to the gravity forces. So we can write down this as inertia forces by gravity forces. Now this can be written as, this we already discussed. So this comes out to be V square by GL. Can be written like this. Although this is sometimes defined as a Froude number, this one, it is more common to use the square root so that V is in the first power. So commonly how we write down the Froude number, we write down in this way. So we already discussed this. And now in this case, you remember that this L, which is the characteristic length in open channel, we consider this as the depth of flow. Clear? So where we have to consider the Froude number, which is also a pure number, it is the ratio of the two forces. So it is a pure number, no dimensions, dimensionless number. That's why we say that it is a Froude number. Now, systems involving gravity and inertia forces include the wave action set up by a ship, the flow of water in open channels, the forces of stream on a bridge pier, the flow over a spillway, the flow of a jet from an orifice. You already studied about practical about this orifice and jet apparatus. Now these are some of the examples where we have to consider the Froude number in the analysis. We have to see that these forces are gravity and inertia forces. These are significant forces. Now once you identify that, okay, for this given fluid mechanics problem, I need to consider the Froude number, then when we want to ensure, clear, to compute the Froude number, as I said, the length L must be some linear dimension that is significant in the flow pattern. For a ship, it is taken as length at the water line. Now those people who study naval architecture, so in that case, this L in the Froude number that you see here, as I already discussed here, this L, what they will consider. So that is taken as length at the water line. For an open channel, which we studied so far, it is the depth of flow. So you can see here it depends on the nature of the problem. Now for situations where inertia and gravity forces predominate, dynamic similarity occurs when the Froude number is the same in both model and the prototype. This we have to ensure. When the Froude number is the same in the model and in the prototype, then we will say that the model and the prototype, they are dynamically equivalent, or dynamic similarity exists between the model and the prototype. And then we can transfer the results between the two. Now you can see here, watch another video just for understanding purpose here. You see here that there is a liquid in this bottle and it is rotated. So what will be the effect of gravity? You see that the effect of gravity is to flatten out this. If you stop rotation of this bottle, what will happen? It will try to flatten the surface. You see the water in a bottle, it has the flat surface. That is the effect of the gravity. Clear? That the gravity tries to flatten out the surface of this liquid. So it means that in such cases the Froude number has to be significant and must be considered. Clear? This is important. Let me just go for one more slide, then I will stop it here. You see that incomplete similarity that we already studied, if you remember the geometric similarity that we consider, we studied that it is not always possible. It is not always possible. So similarly, we say that complete similarity is achieved only if all the three conditions of similarity are met. But this is not always possible. We already studied for the case of river models, because in that case complete geometric similarity is not possible. So that's why complete similarity is achieved only if all the three conditions of similarity are met. So models for which one or more similarity requirements are not satisfied are known as distorted models. This is what we studied earlier, that these are known as distorted models. Clear? It doesn't mean that now we cannot apply the similitude and transfer the results. No, we have other ways to solve the problem. We use distorted models. Now, achieving complete similarity is particularly a problem with the Reynolds number. Now we come to this dimensionless numbers. I will explain with an example that sometimes it is also not possible to ensure complete similarity. What we have to do then? So using the same working fluid would require a velocity ratio inversely proportional to the length scale ratio. And hence, because you see velocity length there, you see here in case of Reynolds number, if I come back to the Reynolds number here, you see that if we, okay, let me go to the two where we compare. Now you see here, if you compare the ratios, so they are inversely then related. Clear? They are inversely then related. I will show you in the problem also. Example. So using the same working fluid would require a velocity ratio inversely proportional to the length scale ratio, and hence what will be problem? Impractically large velocities in the scale model. If you want to satisfy the Reynolds number, we have to face these type of issues. This may not be practical that you can ensure very high velocity values in the model. A velocity scale fixed by, for example, the Froude number means that the only way to maintain the same Reynolds number is to adjust the kinematic viscosity substantially. The requirements is that if you want to use different fluids that should have that kinematic viscosity, is that practically available to us or not? It is not that you just provide any fluid. No, you have to then use the fluid that meets the criteria. So let's say if you get a value of the kinematic viscosity and practically there is no fluid available which has that viscosity, then what we have to do? So that's why when we ensure the dynamic similarity, sometimes it is not possible to ensure complete similarity. So in this case, what we do? Let me just give you this example. So in this case, you see that we have a prototype here. This is a prototype, and this is 1/20th scale model. This is the scale model. So now in this scale model, for ship hydrodynamics, those who study naval architecture, ship hydrodynamics, if similarity is maintained, while R, the Reynolds number is allowed to be different, because you cannot maintain at the same time. So what they do is that they allow F similarity to be maintained, while R is allowed to be different. Why? Let us compare the two. What the two says, you will get the idea. You know, we have to ensure that the Reynolds number in the prototype should be the same as the Reynolds number in the model. So when you simplify these two, this is what we get here. This is what we get here. When we ensure the Froude number in the model and the prototype, then this is what you can get from here. These are simple, you get here. Now when you compare the two, what we get? To match both R and F, viscosity in the model test is a function of scale ratio. You get this result. This is not feasible. You see, this is what we get. that the viscosity here, this ratio, this becomes a function of the scale ratio, length scale ratio. This is not feasible. So that's why in such cases what we do is that we allow the Froude number that is maintained and let R vary. So how we do it? Let me just say that how we do it. So what we do is that the usual technique is to operate the model so that satisfy one of the dimensionless number, which is the Froude number here, and then to correct the results with experimental data dependent on the other dimensionless number. So what we do it, we first allow one to occur and then we have to correct it for the other using experimental data. For example, the ship that we consider here. So in the case of a ship, the model will give the total resistance because we measure the resistance that is offered, as you saw the video also in the towing tank. So you see resistance will be offered to the movement. So this will give us, the model will give us the total resistance, from which we must subtract the empirically computed skin friction to determine the wave making resistance of the model, because we allow the Froude number similarity to be maintained. So that is due to the gravity. So the gravity waves effect we only want to bring. So from the total resistance, the empirically computed skin friction needs to be subtracted to get the wave making resistance of the model. From where it will come, we already studied about this, forces on immersed bodies, how to calculate the skin friction, that we already studied. So from there you will calculate and subtract from the total resistance, so we get the wave making resistance of the model. Now then, by using the Froude number criteria, we can determine the wave making resistance of the prototype. Now using the Froude number, which must be the same for the model and the prototype, we can determine the wave making resistance of the full size ship of the prototype, and then you can add the computed skin friction for the prototype to obtain the total resistance for the prototype. This is how then we solve the problem. So we will continue with this discussion in the next lecture.